everyone. I am Janakee, and I am postdoc at Tata Institute of Fundamental Research, Mumbai. And this work was done with Dr. Girish Kulkarni, also at TIFR. So today I'm going to talk about the implications of the Lyman alpha forest at redshift 5 on the 21 centimeter signal from the epoch of reionization. So because of latest observations in the Lyman alpha observation spectra at the high redshift quasars between redshift 5 and 6, we have been able to make a large catalog of the uh, effective optical depth of these Lyman alpha forest at these redshifts. So between redshift 5 and 6, we can see that the Lyman alpha optical depth has very large scatter, which means that which indicates special fluctuations in the ionized state of the IgM at the same redshift. So for this, it was difficult to explain these observations using the standard models of the reionization, in which we assumed the uniform UV background. So for that, Kulkarni et al. In 2019 has given this reionization model, which is a model of late reionization, in which is able to explain this effective optical depth of Lyman alpha forest very well. And looking at the light cone of this late reionization model, we can see that there are very large neutral regions, neutral patches at very low redshifts, even at redshift 5.5, which these patches are of around 100 megaparsec, as large as 100 megaparsec, which means that these add into the fluctuations of the neutral uh, uh, this add fluctuations into the neutral regions, which corresponds to the special fluctuations of effective optical depth of Lyman alpha. So here we show this reionization history of this model, and we can see that the reionization is midpoint is around 7.1 and it ends at around redshift 5.3. This model also seems to in agreement with other observations of the IgM state at this redshifts. So um, compared for a contrast, we have also shown early reionization model, which is given by for that we have chosen Hart and Meadow model of 2012, which ends reionization at redshift 6.7. So now, because of the improvement, because of the change in the reionization optical depth, CMB optical depth given by Planck, we can see that the late reionization model also seems to fit the latest Planck data. And whereas the earlier reionization was predicted sooner because of the Planck reionization optical depth. So now, because of this presence of these large neutral islands at low redshifts, we can see that even in the brightness temperature, there are large patches which seem promising for from observational perspective. So looking at the global brightness temperature, we can see that even at redshift less than 6, there seems to be a large brightness temperature global signal. And here, by the way, for the rest of the talks, for the rest of the talk in this work, we have assumed that the spin temperature is much larger than CMB temperature, so the heating has saturated. If this assumption is correct, like very good assumptions at this low redshifts, but if it was not, if there were fluctuations because of spin temperature, then that would probably add into the spin temperature into the brightness temperature fluctuations, which we are already showing. So this is like a conservative approximation. So these comparing the early and late reionization models, I'm showing power spectra of ionization at on the left and brightness temperature on right for a range of K values from around 0.1 to 10 H megaparsec inverse. And at redshift 9, between these two models, there doesn't seem to be a drastic difference other than the fact that there is larger power at small K modes, which corresponds to larger reionization bubbles. but and there is similar trend in the brightness temperature power spectra. However, comparing the same two models at lower redshift, at redshift 5.6, you can see that there is orders of magnitude difference in the brightness temperature power spectra. And most of the power in the brightness temperature in the early reionization model comes from the density fluctuations, because the ionization fluctuations are like completely negligible. So basically, the thing is that if the reionization is patchy and if it has been delayed, then there is large power at even at low redshifts in the 21 centimeter brightness temperature power spectra. So then the question is whether this can be observed. So observation between 5.4 to 6 corresponds to smaller, corresponds to high frequencies like to around 200 to 220 megahertz. And this is better for observations because foregrounds are weaker at high frequencies. So for this analysis, we have used 21 centimeter sense given by Pober et al. And to analyze the sensitivity of four radio interferometric observations: MWA, LOFAR, HERA, and SK1 low, for 1080 hours of observations, which about 180 days and 6 hours per day. And we have assumed that the moderate foreground models, which means that the foregrounds are confined within the wedge. So this is again the power spectra of the late reionization model. And what we see is that HERA and SKA should be able to detect this signal, has enough sensitivity to detect the signals at redshifts 5.6 for the late reionization model. And uh, whereas this is similar trend is held between all the redshifts, between say redshift 6 all the way from redshift 6 to redshift 5.4, that HERA and SKA have enough sensitivity for 1080 hours of observations to be able to detect this signal. Now let us see what are the current observational limits. Here I have shown the here basically the brightness temperature power spectra evolutions from all the way to redshift 10 to redshift 5. And this is for the early reionization model, in which was ending at redshift 6.7. And I've shown three K values. So the first one is at 0.08 H megaparsec inverse, which corresponds to the purple line. Then red, which is 0.2, and the yellow line, which corresponds to 0.5 H megaparsec inverse. And we have had a number of excellent observational constraints, limits at this over the years, from GMRT, paper, MW, and LOFAR. And these results have improved over the years. So at low redshifts, we have constraints from MWA, and at intermediate redshifts, we have from LOFAR, which are the best current upper limits. However, we don't have much observations at redshift lower than 6, because when these observations were planned, most of the assumed reionization model was this early reionization model, which which predicted that the reionization would have ended by redshift 6 or to 6.5 or 7, between that. But now our latest data from the Lyman alpha forest suggests that the reionization ends late. Therefore, there is considerable power between redshift 5 and 6 at this K values. And it would be interesting to see the future observations like HERA and SK try to probe these K modes, these scales at these redshifts between 5 and 6, because the information that we get from Lyman alpha forest is incomplete, because it saturates at for high neutral regions, whereas the 21 centimeter will be able to show us the evolutions of the ionized regions. So they should complement. So in summary, basically conclusion, I'd like to say that the large fluctuations, special fluctuations in the effective optical depth of Lyman alpha forest suggests that the reionization is late and it's patchy. It ends at redshift 5.3, where which means that there is large power in the brightness temperature of the 21 centimeter signal at redshift 5.4 to redshift 6. And this enhanced power should be able to be detected by SK1 low and HERA for 1080 hours of observations and optimistic foreground models. So I'll stop here. Thanks.
Thank you very much, Janakee.